So there is a mailing list for this seminar. It is on the seminar page, I'm pretty sure. If not, it will be there in about 5 minutes. And so for announcements of the talks, et cetera, trying to keep this fairly low overhead, and so there aren't going to be lots of spam messages or anything. That's number one. Number two, here's an interesting project thought, which is it turns out that Stanford is in the process of potentially deploying a bunch of Bluetooth-enabled locks. So smart connected objects for locking doors. Turns out that they're sort of looking at the technology, et cetera. If you're interested in seeing how to hack these and compromise them, if you talk away, Stanford would very much like to know. And so Amit Levy has been chatting with the folks at Stanford who are doing this. And so this sounds like something you'd like to do, like pull these things apart and see how you can maybe show that they're not in fact secure. Chat with and me. So our talk today, so one of the things we've been talking a lot about in the context of the Internet of Things is this question of whether or not we can sort of break apart cryptography from being this black or white, confidential or not confidential. This idea of being able to compute on confidential data, being able to compute on encrypted data. This is a relatively new topic, or it's not a new topic, but a pretty hot and interesting topic in cryptography today. So I thought that one of the best things to do would be to have the first sort of the research-focused talks in the seminar be exactly on this topic. And so David Wu, who's a PhD student here at Berkeley, working under Dan Boneh on applied cryptography, volunteered to sort of let us know what are things like today with computing on encrypted data. So please, let's welcome David Wu.
Cool. So thanks, Phil, for the introduction. So I'm actually a PhD student at Stanford working with Dan. And I'll be talking about homomorphic encryption and how we can compute on encrypted data with relation to the Internet of Things. So I feel like I should start with the Internet of Things example. So consider your typical smart home today. And suppose it has many devices all connected to the Internet. So we have these smart light bulbs, we have smart thermostats, and so forth. So all of these things are now generating data, and they're presumably offloading them to the cloud, and the cloud will do something interesting with them. So the Internet of Things is really a way for us to enable a lot of new interesting applications. So let's take a look at one of them. So suppose we have all of these power devices in our homes, and they're all measuring the power consumption, and they're going to offload it to the cloud. And now why does the cloud need this information? Well, the cloud might then do some aggregation and some analytics on the data that's being collected from, say, a neighborhood of smart homes, and then it's going to generate some report. And this report can then be given back to the individual users, the people that live in the smart homes, to help them sort of optimize or recommend suggestions to how they can sort of improve their energy efficiency. So this is one possible example of using or leveraging the power of these interconnected devices. So when we talk about the power of the cloud, what is it really that we're interested in? And I think the answer boils down to big data. We have so many of these devices that are now connected to the Internet, and they all are equipped with sensors, and they're all collecting data. And they're going to all put it into the cloud. And what the cloud can do with this amount of data is that it can now provide us interesting analytics. It can provide us recommendations in the form of recommendation systems. It can allow us to personalize our products to suit our particular tastes. So there's a lot of data being funneled into the cloud, and that's allowing the cloud to give us some new benefit that we couldn't do before. But this is also a very interesting attack surface now. There's now this individual personal user information that's living in the cloud. Well, as an adversary, I would like to compromise the cloud and potentially get a hold of this user information. So with a lot of big data, we had very big attack surfaces and lots of incentives for adversarial use. So the question that security researchers and cryptographers would ask then is, can we still provide this service? So we want to provide this useful service from the cloud that's being able to take advantage and compute on all of this data. But at the same time, we want to preserve the privacy and confidentiality of the data that enters the cloud. So that's sort of the overarching goal that we want to achieve. So the first solution that cryptographers might propose is something called secure multi-party computation. So in the standard context of secure MPC, we have multiple parties, and they want to compute some joint function on their private inputs. So let's look at an example. So let's consider this smart home example, where we have a group of smart home owners, and they want to compute their average power as consumption. And so they can sort of see, are they using more power than average? Are they using less power than the average user? So in this case, the private input would be the individual power assumption of each smart home. So all of their devices, they measure how much power they're consuming, you aggregate that, and they will now want to compute the average over all of these things. So in a secure multi-party computation context, basically all of these smart home owners, all of these users in the multi-party computation, they're going to interact, they're going to communicate, exchange some information, and at the end of the computation, each party will learn the average power consumption and nothing else. And the privacy guarantee then is that no party actually learns anything about the other party's inputs other than what can be directly inferred from the output of this computation. So clearly, user A, upon participating in a computation, learns the average power consumption. And the average implicitly reveals some information about the power consumption of the other users that participated in a multi-party computation. But the privacy guarantee is that you don't learn any information beyond this. And there's a very precise way that we can formalize this cryptographically, but I won't get into that. But this is like the general idea behind multi-party computation. So I'm just going to drill down into a little more details. So let's consider first a simpler example of multi-party computation. Rather than having multiple parties, let's just consider having two parties. So two people want to compute some private function on their inputs, and some function on their private inputs. So more or less, this is a solved problem. So it was solved more than 30 years ago with the work of Andrew Yao. And basically, Andrew Yao proposed a garbled circuit. And garbled circuits, in a garbled circuit, what we do is we express the function that we want to compute as some Boolean circuit. And then he gave a protocol to privately evaluate this Boolean circuit. And the way this works is sort of like this. So this is two parties. So let's say we have party A and party B. And they want to compute some function. So the way it would work is that party A will first take the circuit. So we assume that the function they want to compute is public. So the function in this two-party computation might be which of us is expending more power this month. So that could be one possible application here. So basically, the circuit that they will compute is now a greater than circuit. So is party A's power consumption greater or less than party B's? So we take the comparison circuit, and we apply a transformation to it. We produce a garbled version of the comparison circuit. And the way you evaluate a garbled circuit is you get garbled inputs corresponding to each bit of your input. So let's say party B's power consumption is the number 3 for whatever reason in some units. So then the bits of party B's input would be 1, 1 in binary. And the way that party B was to evaluate the garbled circuit is it would ask party A, who prepared the garbled circuit, for the inputs that would correspond to his bits. And the way that he requests the inputs is using an oblivious transfer protocol, which ensures that party A does not learn which bits of input that party B requested. And party B only gets the garbled inputs for his particular request. And now you can evaluate the garbled circuit. And once you evaluate the garbled circuit, by the construction of the protocol, which I won't get into too much detail, but it allows party B to eventually learn the output of the garbled circuit, and therefore the output of the computation. And hopefully party B is honest, it will inform party A what the output is. OK, so that's sort of the general framework when we work with two parties. So the high-level idea, one party prepares a garbled circuit, one party evaluates it. OK, so to sort of get a feel for how efficient these operations are, Yao circuits are very efficient, and they're very heavily optimized. So in 2013, SDCS, Asheroff et al. Demonstrated that we can now evaluate circuits with 1.29 billion gates in 18 minutes. So this is basically evaluating one gate at the microsecond level. So compared to what I'm going to tell you later in the talk, this is extremely fast. So just as a sort of a more technically inclined point, Yao circuits provide semi-honest security. So this is basically security when we assume that both of the parties participating in a computation, they will follow the protocol as written. So they will do everything you tell them to do. But at the end, they might look at all the messages they receive and try to learn something about the other party's input. So semi-honest secure means that they don't learn anything they're not supposed to by looking at the transcript of the communication. And but usually in security, that's not all we care about. We want to care about malicious adversaries who might do arbitrary things and deviate from the protocol in order to achieve some objective. So it turns out that we can actually take Yao's garbled circuits and use a cut-and-choose mechanism to achieve malicious security. So it is possible to generalize Yao circuits to achieve malicious security, but this will not be as efficient. So this number cited here is for the semi-honest setting. But it is possible, and it is still pretty efficient. OK, so the question, though, when we talk about the Internet of Things is that What happens when we have 3 parties? What happens when we have 1,000 parties, 100,000 parties, right? Because chances are we have so many devices that are interconnected, it's not going to be 2 parties participating in the computation. It's going to be many parties. So what we really have to look at is general multi-party computation. And it turns out that this problem is solved, in quotes. And what does that mean? So I'm going to, so Goldreich, Macaulay, and Wittgerson in 1987 devised the protocol for doing general multi-party computation for arbitrary Boolean circuits. So again, for arbitrary functions. And a high-level idea of how this works is that in the first step of the computation, all of the parties that are participating are going to exchange some information. They're going to sort of split their input and secret share it across all the parties in the network. So already, if you think about the Internet of Things example, when we have thousands of parties, this is starting to look infeasible. Now we need 1,000 parties. All of them need to talk to each other, so all the pairwise connections, and they all need to share their inputs. But that's the first step of the protocol. In the second step of the protocol, we're going to devise a way to evaluate each gate of the Boolean circuit on these split secret shared inputs. So basically, we've reduced the problem of evaluating general functions to basically just sub-protocols for privately evaluating like an AND gate or an OR gate on private inputs, or secret shared inputs in this case. So I'm not going to go into further details since this is not really the subject of the talk, but this is sort of a high-level blueprint of how we achieve general multi-party computation for arbitrary functions. So the way I like to view these results is that this is really a feasibility result. This is a really nice, very elegant theoretical result saying that any arbitrary function we can securely evaluate on private inputs. So that's really nice. But in terms of practical, this is really not cutting it. And here are some reasons why the general multi-party computation may not be ready for, let's say, prime time, especially in the Internet of Things. So first, there's going to be many rounds of communication and interaction with these multi-party computations. So when you have complicated functions, basically for every gate of the circuit that we want to evaluate, we're going to have to communicate, exchange bits of information. So this is not great when you have many devices. Secondly, there could be many very large bandwidth, right? Because if we're communicating on every gate in a circuit, and let's say I'm evaluating a moderately complicated function where there are tens and hundreds of thousands of gates, this is potentially a lot of bandwidth being exchanged. And this sort of blows up with the number of parties as well. And the last thing that I think is particularly relevant in the case of the Internet of Things is that it's very hard to coordinate interactions when you have a large number of parties. So particularly, let's say we have a neighborhood of smart homes, and they all want to communicate, and they all want to compute the average. Well, it might be the case that they don't even know who all the parties are in the computation a priori, right? They know they want to compute it with all the other parties in the neighborhood, but they may not be able to say, oh, here is the first party, here's the second party, how do we exchange inputs? So it's very hard to coordinate interactions. So, and then there are other considerations that I'm not going to discuss. So issues of fairness, issues of guaranteeing output delivery. So these are issues that come up when we look into the details of secure multi-party computation. But there are other considerations, just putting those out there. OK, so that's not the focus of this talk. The focus of this talk is actually on homomorphic encryption. And the way that I want to sort of visualize this is on a spectrum. So when we want to do secure computation in crypto, there are basically like 2 competing ways of doing it. So on the one hand, we have the GMW protocol. We have this general multi-party computation. And these protocols are sort of characterized as having many rounds of interaction. The way that we compute is we have all the parties get together. They're going to exchange some bits of information. At the end, they're going to learn the output of the computation. And these are typically restricted to Boolean circuits. So on the other end of the spectrum, we have homomorphic encryption. And the nice thing about homomorphic encryption is that it requires very few rounds of interaction. And I'm going to give you some very precise examples that show that we don't have this interaction blow up. We don't have, potentially, this blow up in bandwidth or in coordination that we see with general multi-party computation. So this is particularly important when a number of devices get really large, when the number of parties that want to participate in a computation is huge. And typically, homomorphic encryption operates over arithmetic circuits rather than Boolean circuits. So Boolean circuits, the building blocks are AND and OR gates. In arithmetic circuits, the building blocks are basically addition and multiplication. So I can add numbers, I can multiply numbers. So I'm working over numbers here, generally working over bits there. So of course, there are arithmetic circuits that also fall on this side of the spectrum. But in general, this is sort of the dichotomy. And in the middle, sort of we can hybridize these approaches. We have custom protocols. So we sort of combine the best of both worlds. And so I think that custom protocols in general win. But if we have to design a custom protocol for every function we evaluate, that's going to blow up astronomically. So this is probably not going to be feasible for doing general computation. So when we want to do a general mechanism for privately computing, then either we would look at MPC or homomorphic encryption. OK, so let me define what homomorphic encryption is. So homomorphic encryption scheme is an encryption scheme that allows you to do operations on ciphertexts. So what does that mean precisely? We can sort of formalize this or view this as consisting of 3 functions. So first, we have an encryption function. So this is your standard vanilla public key encryption function. It takes in a message M. It takes in a public key. It produces a ciphertext, exactly as you would expect from an encryption scheme. Nothing fancy. Similarly, there's a decryption function, because if we can't decrypt, then it's not very useful. So we take the ciphertext. We take in a secret key. So this is a secret key function. This is a public key function, in contrast. And it produces the original message M. So the correctness property from an encryption scheme is that if I encrypt a message M and I apply this corresponding decryption function, I better get the same message M back. Otherwise, it's not very interesting. The more interesting notion, other than correctness, is semantic security. So semantic security says that if I encrypt 2 messages, possibly adversarially chosen, you can't distinguish. You can't figure out which message I encrypted. So that's what we mean by secure. OK. So far, I've said nothing that would sort of distinguish homomorphic encryption from, say, public key encryption. So the third function is the distinguishing factor. So the homomorphic encryption scheme consists of an evaluation function. An evaluation function, for now, it will be parameterized by some function f. So f might be the addition function. So it might be f of ab equals a plus b. Or it could be a multiplication function, f of ab equals a times b, and so forth. So what does the evaluation function do? Well, it takes in many more inputs. It takes in 2 ciphertexts, first of all. So it takes in a ciphertext C1, that's an encryption of a message M1. Takes another ciphertext C2, that's an encryption of M2. And it takes in some evaluation key, which might be the public key or might be nothing. Sometimes we don't need an evaluation key. But just for generality, it's possible to require an evaluation key. And what it produces is another ciphertext C3. So it takes in 2 ciphertexts and produces a new ciphertext. But what is interesting is that now when I apply the decryption function to the output of the evaluation function, I basically get the original function f that I'm homomorphic with respect to evaluated at the inputs. Does that make sense? So suppose f is an addition function. I can encrypt 2 numbers, let's say a and b, and I apply evaluate. I'm going to get an encryption of the value a plus b. So when I decrypt, I get a plus b. But notice that I'm able to do this operation only on the encrypted data, only on the ciphertext. I do not need to decrypt at any point in this operation. And that's where the power of homomorphic encryption comes in. Yeah, question?
Do those messages have to come from the same encryption key?
So the question is whether the messages have to come from the same encryption key. And generally, yes. They must be encrypted under the same public key. And then we can homomorphically operate on them.
So how does that work if 2 different homes are encrypting their sensor data?
OK, so I will get into that. Yeah, hold your thought. But that's a very good point. OK. So there are, in fact, many homomorphic encryption schemes. So for instance, as I mentioned, the Al-Gamal encryption scheme is homomorphic with respect to multiplication. So it allows us to multiply on ciphertexts. The Paet crypto system is homomorphic with respect to addition. So we have another operator. And there's a homomorphic operation that allows you to add 2 numbers together. And as you might imagine, Paet is actually very useful for applications in voting, for instance. Because when we want to vote securely and privately, we basically need to add up a bunch of counts. So Paet crypto system is suitable for many voting applications. OK. But so far, at least in the 2 examples I've given so far, the function f is one function. It's either multiplication or addition. So the natural question to ask then is whether there's a homomorphic encryption scheme that's homomorphic with respect to more than one function. So in particular, homomorphic with respect to 2 operations. What if I want to add and multiply? I don't want to just add. I don't want to just multiply. I want to do both. And the reason why this is interesting is if you think about it, if we can do addition and multiplication, let's say over bits, over the finite field f2, what I can do is I can view an addition gate as computing an XOR. Because if I compute the sum of 2 bits mod 2, that's basically evaluating an XOR function. And similarly, multiplication in f2, I'm taking if I have bits as my inputs, then a multiplication basically computes an AND gate. And an AND gate and an XOR gate are complete for the class of Boolean circuits. So a fully homomorphic encryption scheme allows us to homomorphically compute any Boolean circuit on the inputs. And this is basically the way that why we say that fully homomorphic encryption allows us to do arbitrary computation on encrypted data. Because you can just express your computation as a Boolean circuit and homomorphically evaluate the Boolean circuit. So this was an open problem. So this was actually proposed in 1978, right after RSA came out. And for more than 30 years, this has remained an open problem in crypto. So the first progress that we made was in 2005 with the BGN crypto system. And the BGN crypto system is what we would now call a somewhat homomorphic encryption system. It allows us to do is additively homomorphic, so we can do as many additions as we want. But it has one limitation: we can only do one multiplication. We can't do two multiplications; we can only do one. So, but it's a lot. It's a pretty substantial progress, because before we can only do one operation, either addition or multiplication. Now we can kind of do both. We can do a lot of additions. We can do one multiplication. And in 2009, Craig Gentry, in his PhD thesis, he basically gave the first construction of actual fully homomorphic encryption. And his original construction was based on ideal lattices. OK. So now I'll get to the question of how we can actually use homomorphic encryption to do useful computation. So consider the case of do we want to do privately outsourcing computation. So this is sort of the standard example when we talk about homomorphic encryption. And this is an example where we really want to leverage the computational power of the cloud. So we have all of these smart devices here. And usually they're going to be computationally bound. But they want to do some computation. They're collecting a lot of data. And maybe they want to do some statistics or some aggregation on the data. So the way that it will work with homomorphic encryption is that first, each of these devices, they will take their data, and they will encrypt it and send it to the cloud. And now it doesn't matter whether we trust the cloud or not, because all the cloud ever sees is encrypted data. And the cloud will homomorphically compute on it. So with a fully homomorphic encryption scheme, I can compute any function that I can express as a Boolean circuit. So in particular, I can do any kind of statistical analysis I want directly on the encrypted data. And at the end, it's going to send all of that encrypted data back to the user. So in this case, the public key that they will use will be the user's public key. So all of the devices for one user, they will encrypt to that user's public key, send it to the cloud, do the computation. User decrypts the underlying model. So this is your sort of your canonical example. OK. So another example is sort of doing machine learning in the cloud. So I'm going to come back to the example I gave at the beginning, where we have a bunch of smart homes now. And they all want to learn something about, let's say, the average energy consumption of all the homes in a general area. So how do we do machine learning in the cloud? Well, so first, we have to say someone has to publish the public key. So in this case, I'm going to say the power company publishes the public key. And all of the smart homes that want to participate in this computation, they're going to take their data, and they're going to encrypt it under the power company's public key. So this is kind of a little odd, because now the power company can learn the individual power consumption. But presumably, the power company might already know that information. So this is not a huge loss in privacy. But I'm going to formalize that in a little bit. So now the cloud, again, we don't have to trust the cloud well, we have to trust the cloud somewhat. I'll say exactly why we need to trust the cloud. But the cloud will now compute the model homomorphically. So whatever model the power company was interested in, it could be some kind of linear regression model, it could be some other more fancier machine learning model. But it will compute some function on the encrypted data from each of these smart homes. And it will send the resulting model to the power company. And now the power company will decrypt and get the model. So this is how we can sort of do machine learning in the cloud. OK. So now let's consider, what does an adversary see? So suppose now the cloud is compromised. So our adversary now sits on the cloud. And basically, because of the security, the semantic security of the homomorphic encryption scheme, this adversary right here always sees the ciphertext. And ciphertext cannot reveal any information about the underlying plain text. So therefore, a passive adversary that sits on the cloud does not see any client data. So I have to be a little careful in saying that it's a passive adversary. So an active adversary can do various things. It can't compromise the privacy, but it can cause this computation to fail. So we're going to just restrict ourselves to a passive adversary. So if your cloud gets compromised, at least you don't lose user information. Your computation might be jeopardized. And there are other ways that we can prevent that. But that won't be the focus of this talk. OK? The next, question. it can cause the wrong answer. So for instance, suppose the adversary is dictating what the cloud is computing. Well, it can just replace that function with, say, computing a 0 function. And now the power company will always get 0. And so now the computation is wrong. But yeah, that's a good point. OK, so the second observation that we have is that the power company there, they only obtain the resulting model. So as long as the power company and the cloud do not collude, then any of the individual user information is actually preserved. So we have to make a weak non-collusion requirement if we want to say the power company should not be able to see the individual data. And the last thing, which I think is the most interesting point, at least when we look at the Internet of Things, is that look at who the parties have to communicate with. It's only one party, only the cloud. And the only thing they need to do to participate in this secure computation is they just need the cloud's public key. They do not need to communicate. They don't even need to know who else is participating in the computation. So this is essentially has resolved the issue of this interaction blow-up that we see when we talk about secure multi-party computation. And this, I think, is the main selling point for using homomorphic encryption for doing these kinds of computations. OK, so now there's a natural question now. So I said in a previous slide, if you look at how I presented the model, all of these different devices, these smart homes, they're all encrypting their data homomorphically and sending them off to the cloud. And homomorphic encryption is public key encryption, so it's slow. In fact, it's much, much slower than public key encryption. So it seems like we're not really making much progress, right? Ideally, what we want to do is we want to be able to encrypt our data, which there might be a lot of, right? Because we have a bunch of sensors, and they're collecting data, let's say, in real time. And we want to offload them off to the cloud. And if every homomorphic encryption operation takes a minute, well, we basically throw the real-time aspect of it out the window. So what we like to do is be able to use AES to encrypt or use some kind of symmetric crypto to encrypt our data before offloading it to the cloud. And the question is, can we do something like this? So with public key encryption, we have a solution for this, which is basically key encapsulation or hybrid encryption, where basically what we do when we want to encrypt a lot of data using a public key is we generate a random AES key, a symmetric key, encrypt that using the public key, and then encrypt the payload with the AES. So we can take advantage of the speed of symmetric primitives in conjunction with the public key nature of the crypto system. So this can be unsuitable when we have large volumes of data, which presumably is a very, very possible consideration when we have a lot of devices that are just basically monitoring, collecting data, and sending it off to the cloud for processing. So there is actually a way that we can achieve hybrid homomorphic encryption. So I think this is pretty relevant when we talk about the Internet of Things. So let's just do the standard thing. Like, let's just do what we do when we talk about how to do public key crypto for large amounts of data. Well, what we're going to do is we're going to encrypt the AES key using the homomorphic encryption. So this is expensive, but the AES key is short. It's 128 bits. So we're going to encrypt an AES key. And we're going to do exactly as we do in all other hybrid encryption schemes. We're going to encrypt our payload, our message, using the AES. So M here is presumably large. OK? So now the question is, well, AES is not homomorphic. At least, hopefully, AES is not homomorphic. And so it seems like what we've done is we've lost the ability to compute on the encrypted data. So this doesn't look like a very good solution. But what if we have a fully homomorphic encryption system? Well, it can evaluate an arbitrary function. And if it can evaluate an arbitrary function, well, the AES decryption circuit is also a function it can evaluate. So what do we homomorphically evaluate AES in the cloud? So what do? We send the encryption of the AES key under the homomorphic encryption system, and then the AES encryption of the message to the cloud. The cloud will take the AES encryption of the message, and the first thing it will do is it will homomorphically encrypt that. Because the homomorphic encryption is a public key system, the cloud does not need to know any additional information to perform this step. And now I'm going to homomorphically evaluate the AES decryption circuit. I'm going to take the encryption of the AES and the encryption of the AES key, and what I produce is basically, homomorphically, I'm going to apply a decryption function to this argument right here, and that just gives me M. So now I have a homomorphically encrypted M. So it's as if the client had given a homomorphic encryption of M to the cloud. Yes?
So all you've done is move the computation. You still have to do the expensive computation of doing the homomorphic encryption.
Mm-hmm.
You're just not making the device do it.
Right.
Somebody else do it.
Right. So we assume usually that the cloud is much more powerful than a device. So if the cloud is more powerful, it has more computational resources, we want to sort of offload the more expensive part of the computation to the cloud rather than have the device do homomorphic encryption of large amounts of data. OK. And now that we have a homomorphically encrypted message, we can apply the standard computation on encrypted data and obtain an encryption of a function evaluated at the message. So recent benchmarks, so just from last week, the best we can do with the AES decryption circuit, we can now homomorphically evaluate AES 128 at a very fast rate of 4 seconds per block. So we're making progress. So 3 years ago, it was about half an hour per block. So we've gotten down to 4 seconds. OK, all right. So I told you how we can use, oh, yeah, question.
I have a dumb question. Does the client get assurance that the cloud is not just decrypting the key and then using that to run normal AES and then just getting the plain text?
Could you repeat the question?
Oh, yeah. So the question is whether the cloud can run AES decryption and recover the plain text. Is that right?
Yeah.
OK, so that doesn't quite work because we have the homomorphic encryption system. So everything is encrypted homomorphically. So there's always an outer layer of encryption. And we're just using the AES decryption key to decrypt the inside. So we have homomorphically encrypted of AES encryption of M. And we're going to evaluate the AES decryption circuit, which can only get rid of the AES encrypted part. We still have the homomorphically encrypted part. And that's still semantically secure.
The private key of the public key that you encrypted. Yeah, but the cloud doesn't have that, right?
That's right. That's right. So the cloud should never have a secret key for the homomorphic encryption system. And in fact, if the cloud did have the secret key, then there's a trivial mechanism for the cloud to compute. It should just decrypt the data and compute on the plain text, which is way, way faster. So in this case, in this example, the power company would have the private key for the system. So either when outsourcing computation, the client would have the secret key. In the case where we're doing machine learning in the cloud, the analyst or the researcher at the end would have the private key for the system. OK. All right. So how do we actually construct FHE? So the first thing to note that, as I've said, fully homomorphic encryption, or FHE, allows you to compute arbitrary functions on encrypted data. And this is actually really hard to construct. And that's why it really remained an open problem for 30 years. So let's sort of be less ambitious for now. Let's try to compute something that's a little bit simpler. Let's start with a somewhat homomorphic encryption scheme. So the BGN system that I described earlier is already somewhat homomorphic. But in general, a somewhat homomorphic encryption scheme allows you to do a limited number of operations. So not arbitrary computation. It might say you can do 10 multiplications and 100 additions, and that's it. And then once you've exhausted that, then you cannot compute anymore on your ciphertext. So suppose we have a somewhat homomorphic encryption scheme. Yeah. OK. So the really ingenious idea that Gentry came up with in 2009 is that it's actually possible to take a somewhat homomorphic encryption scheme and actually sort of bootstrap it or convert it to a fully homomorphic encryption scheme. And I'm going to sort of show the general transformation that makes this possible. And the starting point that we will have is a somewhat homomorphic encryption scheme that is able to evaluate its own decryption circuit. So we want a somewhat homomorphic encryption scheme such that the decryption circuit is pretty simple. It's very easy to decrypt. And such that the homomorphism as afforded to us is actually sufficient to evaluate its own decryption circuit. OK, so the way that we're going to visualize this graphically is I'm going to have, so we have a somewhat homomorphic encryption system. So I'm going to represent ciphertext as these locks. And the shading in the lock will sort of denote how much homomorphism remains in the computation. So here we have something sort of like a fresh encryption. So when I just encrypt the ciphertext, encrypt the message, I can do a lot of operations on it. But as I do more operations, I'm going to sort of move right along this spectrum. And eventually, I'm going to end up with a ciphertext that looks like this, which says we have no more homomorphism. If you try to operate on this, you're going to get nonsense. So that's basically the limitations of a somewhat homomorphic encryption system. OK, so how do we take this and sort of bootstrap it to achieve fully homomorphic encryption? The way that we're going to do this is we're going to define a recryption functionality. So suppose we have a ciphertext that encrypts some message M, and we've done a lot of computations on it, so we can no longer compute on it. So this is the end state of a somewhat homomorphic encryption system. What we're going to do is we're going to do something very similar to our hybrid homomorphic AES. We're going to re-encrypt it. We're going to take this ciphertext, and we're going to encrypt it using our fully homomorphic encryption system, or using our somewhat homomorphic encryption system. And because this is a fresh encryption, I'm going to sort of fall somewhere down here again. Right? It's a fresh encryption. I can do a lot of homomorphic operations on it. So I've taken something here, and I moved it down to here. But now it's doubly encrypted. So this is not an encryption of M anymore. And suppose, in addition, we also have an encryption of the secret key for the homomorphic encryption system. And suppose that the secret key is also a fresh encryption. So we do need a little more information. So given these two things, well, let's just do exactly what we did when we talked about hybrid HE. We're going to homomorphically evaluate the decryption function of the homomorphic encryption system. So I'm going to homomorphically evaluate. So that means doing some applying a function to the inside of the ciphertext. And if I'm decrypting an encryption, what I'm going to get back is an encryption of M. And so this is where we started. But the key note is that this ciphertext allows us to do more homomorphic operations, assuming that this decryption circuit is simple enough. So if we have enough homomorphism to evaluate our decryption circuit, plus one additional operation, plus one additional AND or one additional multiply, we're actually win. We win, right? Because now what we do is we do our computation, we recrypt. Now we can do one more operation. So we apply the one operation once, and then we recrypt, and so on. Does that make sense? So this allows us to take any somewhat homomorphic encryption system that satisfies this property and allow us to transform it to a fully homomorphic encryption system. And we have to make one additional assumption, is that it's OK to give you an encryption of the secret key. So this is a circular security assumption, because we're sort of giving you an encryption of your own secret key to the adversary. OK. So the first bootstrappable construction was given by Gentry in his first construction of FHE in 2009. And since 2009, there's been a whole explosion of works in this area. So there's many, many constructions that sort of have simplified and further simplified and made these things more efficient. And to note, by 2012, these things have been simplified enough so they can fit in a blog post, as Barak and Svika pointed out. And I'm going to give a very brief overview. How much time do I have, actually? Oh, OK. I will not give a brief overview. OK, all right. So let me just give some examples. OK, so this is so the important thing is that FHE actually is pretty slow in practice. So we do have simple FHE schemes, if I had time to highlight one of the constructions. But bootstrapping is very, very expensive. So Halevi and Shoup in 2014, they have these pretty sophisticated implementation. And basically, we can bootstrap one ciphertext in about more than 5 minutes of computation. So if you think that you need a bootstrap on every time you evaluate a gate in a Boolean circuit, this is horribly inefficient and very impractical. So basically, what we have to resort to is using somewhat homomorphic encryption. And so if we can do the computation that we're interested in can be expressed as these simple and shallow circuits. These are more closer to practical. OK. All right. So one of the applications that I want to briefly describe is doing statistical analysis in the cloud. So this was sort of the example I've been trying to motivate throughout the talk. And so now I'm going to show how we can actually do some simple statistical analysis somewhat efficiently using somewhat homomorphic encryption. And so the setting that we're given is suppose all we're interested in is computing the mean or the covariance, so computing the first and second moments of the data. And the nice thing about these types of computations is that for the computing an average, all we need is addition. So this is depth 0. And the depth is measured by the number of multiplications. So multiplications are complicated. They're difficult to perform. So we can sort of evaluate circuits that don't have many multiplications. So for the mean, it's going to be a depth 0. For the covariance, it's a quadratic function. So we need to do one multiplication. We can also do linear regressions on low-dimensional data. So by just evaluating the normal equations. So basically, for n-dimensional data, this is going to be degree n in computation, in the input. OK. All right, let's skip that. OK, so here's one graph that sort of shows the performance of somewhat homomorphic encryption. So this is based on an implementation due to Brakersky in 2012. And basically, it does take a long time. So we have to measure performance on order of minutes rather than on seconds or milliseconds that you might be used to. But arguably, when we want to do this kind of like statistical analysis, you're not going to do statistical analysis in real time. A more, let's say, something that might be more reasonable is that at the end of the day, you sort of run new analytics on the day's worth of data. And so what we really want to care about is how long does it take to run it on a large number of data points. And assuming that we run once per day is actually not too bad. So if it's 1 million data points, it might take an hour of computation on a single core machine. So if you have 64 cores, this graph will actually, you can divide by 64 in the computation time. So then it'll run on the order of a minute or so. Because all the computation here is very naturally parallelizable. Yeah, question?
Does the memory requirement also go up at the same slope?
So right. So I can't quite recall the memory requirement. I think it does go up. So basically, the slope here. Oh, actually, I have some notes on why. OK, so I guess I didn't get to cover batching. But the reason that this is flat is because of a trick that we can use with homomorphic encryption system that allows us to encrypt blocks of data at once. So when we have a small number of data points, it's basically we only have very few number of ciphertext. And so that's why the line is mostly flat. And the runtime really dramatically increases as we increase the size of the data, because we have to now do more multiplications. So this is why this is the characteristic plot. So because the runtime is basically dominated by the number of ciphertext we have to manipulate, I would assume that the memory performance also increases like this. So I think with about 2 million data points, it's about 4 or 5 gigabytes of memory. So similarly, if we're doing linear regression on low-dimensional data, so we restrict ourselves to 2 dimensions, again, we can do something fairly reasonable. So up to about 100,000 data points, we can do it in under half an hour. Again, single-core processing. OK, and similarly, this explains the characteristic behavior of the plots. So before it's flat because of this batching trick where we encrypt blocks. And then eventually, when we have so much data, we're going to have many blocks. And now we have to do more operations on the ciphertext. OK, so there's another application, which is private information retrieval. But I don't think I have time to go over that. OK, all right, so just to conclude the talk. So the Internet of Things sort of brings a lot of new security challenges when we think about having many, many devices, and they all want to participate in some kind of secure or privacy preserving computation. And there are many generic cryptographic tools that are available to do these kinds of things. So if we have only 2 parties, two-party computation is probably the most efficient generic tool we have available. And as we scale up, then we talk about things like multi-party computation, somewhat and fully homomorphic encryption. So as I mentioned, 2-party computation, multi-party computation, these are really, really efficient for a small number of parties. But when we start scaling up to, let's say, web scale, where we have hundreds and thousands of parties, then this is the time to start considering solutions beyond our multi-party computation. So looking at somewhat homomorphic and fully homomorphic encryption schemes. So fully homomorphic encryption is still very, very young. So this was only developed in 2009. The performance of these things have increased by several orders of magnitude since 2009. But obviously, we have a long ways to go before we can actually consider them to be actually practical and viable for the applications we're interested in. And somewhat homomorphic encryption schemes are closer to practical. So if the function that you want to evaluate is simple, i.e. low depths in a number of multiplications, then this might be something that's worthwhile to consider. And there's a lot of big open problems in developing more practical constructions of both somewhat homomorphic encryption as well as fully homomorphic encryption. OK, and that's all I have. So I'll open it up for questions. Yeah.
So, OK, so the real-world construction you had with the power company.
Yep.
So at some point in both models,
Mm-hmm.
the cloud had specifically had the homomorphic encryption of each data point.
Yes.
What happens when the entropy of the data points themselves are small? So in particular, say you're, I don't know, measuring temperature or something like that.
Mm-hmm.
Presumably the entropy in the actual data of the temperature is not 128 bits. It's probably something
OK.
smaller than 32 bits.
Right.
Because that encrypted data is nothing but the homomorphic public key encryption of some discrete number,
Mm-hmm.
relatively limited range.
Mm-hmm.
Can't the cloud just like brute force
Oh, I see what you're saying. So the question is, because the values that we encrypt in practice might come from a small interval. So if, for instance, temperature, if we're going to just encrypt integers, it's going to be a pretty small range. Is it possible for the cloud to just brute force and recover the underlying plaintext? And the answer is no, because of the semantic security of the encryption scheme. So the semantic security says that if I give you an encryption of the number 1, and I give you another encryption of the number 1, they better be different. And in fact, if they're the same, then we have something called deterministic encryption, which is not secure. So the semantic security property ensures that when you encrypt something, even if it's the same value multiple times, you're going to get something different with overwhelming probability. Yep. Question? Yep.
So you're doing research obviously in this area?
Mm-hmm.
I assume you are. So what research questions are you looking at?
OK. So the question is, what research questions am I looking at the moment? So I'm actually not looking too deeply into homomorphic encryption at the moment. So I've done a fair amount of work in the past looking at doing like statistical analysis using homomorphic encryption. But right now I'm sort of shifting towards the hybridized approach where we combine multi-party computation and homomorphic encryption for custom protocols for particular problems. So one particular problem I'm looking at is doing privately preserving shortest path algorithms. So the idea here is that imagine your Google Maps and you want to route from point A to point B on a map. But you don't want to reveal to Google either point A or point B. And you also don't want Google to reveal the routing information in the graph itself. So we want to do privacy-preserving shortest path algorithms. So that's one of the protocols I'm currently looking at. Yeah?
When you talked about getting down from hours to 4 per second or something,
Mm-hmm.
how much of that was algorithm improvement? How much of that was just pure evolution of hardware getting faster?
OK, so the question was, what sort of is responsible for the significant performance improvement from 30 minutes per block for AES to 4 seconds per block currently? So a lot of that is actually due to new algorithmic improvements in the construction of fully homomorphic encryption systems. So in 2009, when Gentry first proposed it, it was based on these hard problems in ideal lattices. And those are, A, hard to implement, and B, difficult to optimize. And so homomorphic encryption systems, over the years, we've gotten a lot of new innovations and developments in improving their asymptotic performance. So that has, I think, probably the vast majority of the improvements there. And then like improvements in data encoding, how we encrypt, and various other functions in both algebraic and algorithmic have led to this tremendous increase in performance. Yeah, question?
It seemed like, so for the numbers that you were talking about, it would be possible perhaps to compute on a single person's data, right? So like 1 million data points. But in the world of big data, it wouldn't be feasible to compute on 1 million data points of 1 million people.
Yes.
But if each person had one data point, they could send some kind of summary to the cloud or to the provider, then they could compute on that.
That's correct. Yes.
So there seems to be some sort of tension there, in a sense of it's not like we can just compute on billions of data points. We have to make some choices about how much is shared and when.
Right. That's a very fair point. So Phil's point was we have to have a sort of hierarchy of how we share the data. So it's not feasible to compute 1 million data points with 1 million users. But it's possible, so if each user sort of individually aggregated their 1 million data points and collapsed it to a single data point, and now we have 1 million users, and now we can compute on these 1 million data points again. So it's a very fair point. So this will sort of go into how we design and how we implement these kinds of protocols. Yeah?
So if I said all the Internet of Things pieces of hardware would have some small piece of hardware in it that could do a homomorphic encryption, some piece of hardware that does, you can tell me only one thing, right? But I'll put it there. You don't have to do this AES thingamajiggy. It just seems to me to be a lose because you're making your life much more complicated, especially in these limited schemes where the total computation is not actually going down.
Right.
Right. And the performance requirements of these embedded things is not that high. It might take me a long time to compute that, but I can compute it probably pretty low energy. So
OK.
if you grant me that, does that change the world any? Does that do you know what to tell me to build now?
OK. So the question is, if we allow what is like the simplest thing that we can have on the embedded devices that would sort of enable these technologies to develop? So yes. So if we really want to, OK. So before I dismiss the AES thing, I think that's actually a pretty viable solution because so the total amount of computation is not going to go down, but it actually might lead to a simpler development. Because what you can think about is in the embedded hardware, all I have embedded is an encryption of an AES key, and that's the only key it uses to encrypt. So it never does any homomorphic encryption. And then all we do when we want to process on the cloud is we just send this encrypted AES key to the cloud along with our AES ciphertext. So I think that's actually, from an implementation perspective, might actually be easier than having to implement in hardware some of these homomorphic encryption operations.
Yeah, I know, but if I think, oh, building something to do homomorphic encryption in hardware is actually not that hard.
Okay.
As long as there's one thing to build that gets put in all these chips,
Mm-hmm.
it's probably not that expensive. So I don't know what the function is.
Okay.
If that was, would that make a big difference or not?
Okay, so I guess in terms of whether that would make a big difference or not, if we want the cloud to not do an exorbitant amount of work, then it would make a very, very big difference. Because if, as I said, homomorphically evaluating the AES decryption circuit is pretty much out of the question from a practical perspective at the moment. Right, so if we just want to do low-degree functions, simple functions, then it's probably best to build in the homomorphic encryption onto the hardware itself rather than doing this AES. But if we do want large volumes and we want to optimize the computation resources on the embedded devices, then it might be better. Yeah, Henry?
What's the cost of doing the homomorphic encryption of an AES key? Is that a huge cost or a small cost?
So it's not a very big cost. So we just have to encrypt we have to basically do 128 homomorphic encryptions, so for each bit of the key. So that can probably be done in about a minute or so. Right, so a minute is a long time, but you're not going to do this in real time. You just need one AES key, and then you can just use the same AES key to encrypt the rest of your data. Yeah?
Are there any homomorphic encryption schemes that don't require the two ciphertexts to be encrypted by the same public key?
OK, so the question is whether there are homomorphic encryption schemes that don't require the two ciphertexts to be encrypted under the same public key. So not that I am aware of. There are key switching transformations that allow you to sort of take a ciphertext encrypted under one scheme and convert it to a ciphertext encrypted under a different public key. And now I can sort of key switch everything to operate on one common public key. But I don't know of any homomorphic encryption schemes, at least native homomorphic encryption schemes, that allow you to do computations on ciphertext encrypted under different public keys.
So let's thank David again.
Okay, cool, thanks.
So we will not be meeting next week because it is Martin Luther King Day, which I encourage all of you to celebrate to honor Martin Luther King. But the week after that, Luca Arapopa, who will be a professor at Berkeley starting next year, an expert in using cryptography for secure systems, like building systems out of these constructions, like CryptDB and Mylar or something for work. She'll be giving a talk on the 26th. And the week after that, actually, we're going to have some guests from Nest talk about their security architecture and the primitives and what the challenges they see in securing the Nest thermostat and Nest account. So thank you very much.